first video of week 10, the final week. All right, so we're going to finish up with R this week, and there should be about 4 videos to go through, and then the test will cover everything that was last week and this week. So today we're going to go over vectors, sequences, and for loops. So to start, we're going to talk about what a vector is. So what we've been working with so far are referred to as scalars. And this just means it's just a single value or a single number. I guess technically they don't have to be numbers, but just a single value. And so we can think of this as having a dimension of 0, kind of like if you have a graph and you have a single point on it, it doesn't have any dimensions to it. And this is in comparison to what we're going to get to today called vectors, which we can kind of think of with the graph metaphor as a line. So it has only one dimension to it, and that's its length. And so we'll get into how to measure length and stuff like that. I'm going to be walking through the examples in our manual that's up on Canvas, the same one that I've been using for all of the other videos. Okay, so starting with example 4.1.1, we're going to make a simple vector. So the way you make a vector is you name it, just like we've been naming our other objects. You use the assignment operator, as we've been doing before, and then you're going to encapsulate your vector in a lowercase c and parentheses. And the C just stands for combine or concatenate, which just means to combine. And so it's basically taking everything in it and combining it into a vector. So here, we just have a simple string of numbers that are printed out. So if we run this, we can then look at what it looks like, and we can see that it's just a string of our numbers. So it's just a simple example of a vector. That's an example of a numeric vector. We can also try a logical vector. So last time we were looking at logical values of true and false. We can also have a vector of those logical values. So if we actually use our vector n that we create up here, we can assign a new vector L to be a logical value for whether or not each element in n is greater than 4. So this means where I just have n greater than 4, it's actually going to do this to each element in n. And we can see that by running that line of code and then looking at L. Okay, so if we look at this, we have a bunch of falses and then 3 trues. If we re-look at n, which I don't need to reprint it, but you can see that 0 is not greater than 4, 1 is not greater than 4, 1 is not greater than 4, 2 is not greater than 4, 3 is not greater than 4, and then the last 3 numbers are greater than 4. So it just ran this command of greater than 4 to every element of n and then passed it to L as a new logical vector. All right, also about vectors. So there's 2 types of vectors. There are atomic vectors and lists. We're not going to get into lists, but the main difference is that atomic vectors require all of the values in them to be of the same type or the same class, really. Whereas lists can have multiple types in them. So let's show class for n. We have numeric. Class for L. We have logical. And so if I tried to take an atomic vector like this and put both a mixture of numeric and logical values in it, it wouldn't work. I can actually show an example of that. Here I will fix n after I do this, but okay. So if we do false, true, and then 1 and 0, we can see that what it did was that it coerced it. So it won't allow false and true to remain as false and true because it's not the same type as 1 and 0. And so what it did was that it coerced our logical values into a numeric value so it could keep everything the same in the single vector. So this is just to point out that, well, two things. First, that R is not going to allow you to use multiple types of data within an atomic vector. And also, I want to point out, which I haven't explained this before, but the numerical equivalent of our false and true values are 0 and 1. So 0 means false, 1 means true. And you can actually see this if you do true times 1, which I know seems weird, you will get the value of 1. If you do false times 1, you will get the value of 0. And that's because trues and falses are read as 1s and 0s respectively in R. So that's more of just a side note. Okay, I'm going to rerun N just to make sure I have the right thing loaded for it. And we're going to move on to example 4.1.3. And this is just to show you that you can also create character vectors. It's not exclusive to logical and numeric values. So if you have a vector, a character vector, they have to be strings that are separated by commas, just as up here our numbers are separated by commas. And commas are just going to be separating the different elements of your vector. So if we run that line, we can see that C is, there are raccoons at UCI. There are indeed. Okay, and if we check the class of it, we can see that it is indeed a character vector. Okay, so this example, 4.1.4, is a long vector. There's actually nothing special about it that makes it a long vector. That's not like some different type of vector. It's more to show you what that number that keeps showing up, that number 1, what that actually means. So if we run this and then print out what C is, oh, sorry. Right, it's not gonna let me do that because it's not a thing. Oh, sorry about this. So let me make this smaller and see if this works, because what I'm trying to do, there we go. Okay, cool. So sorry, my console was too wide before to show what I'm trying to get at. What I wanted to show is that that number is just indicating the position. So number 1 is just indicating that the number next to it is the first number in your vector, or in whatever the thing is that you're looking at. So I wanted to show this example because it has a number 19 down here, and what it's showing is that the number right next to it is going to be the 19th number in whatever string you're looking at. So that's all those numbers mean. They're just data positions, but because they do keep showing up everywhere, I thought it should be important to kind of explain what they are. So yeah, nothing super special, just to show you, because counting, counting every number, especially if you have a big chunk of numbers, gets kind of hard. It's helpful to have those indicator data positions next to it. Okay, so that is it for vectors. Next, we're going to talk about sequences. So sequences are going to create vectors, but they're going to create numeric vectors specifically, and ones whose values are monotonic. So they increase by the same number each time. So to begin, we're going to go over the colon operator and see what it does. So writing out the numbers 1 to 100 is going to be very cumbersome and is actually unnecessary. A faster way to do it would just be to do 1 through 100, or 1 colon 100. If we do that, we can see that the numbers 1 to 100 get printed out, and each value in our vector gets counted, increases by 1. So we have 1, 2, 3, 4, all the way to 100. And we can do this with any numbers. So here we have 1 through 10, gets you what you would think. We can also do this backwards, so R knows how to count backwards. And so they're very similar. However, if you have a larger number than through a smaller number, what it's going to do is count down from that starting number also by an increment of 1. We can see that if we don't specify integers as our numbers, we will still get increments of 1, so 0.5, 1.5, 2.5. So it's still increasing by 1, but you can start it and end it at a number that is not an integer. So you can also see that with this one, we have 0.5 and 10.5. So the difference between them is also an integer. However, if we have the example 0.1 through 9.8, the difference between those two numbers is 9.7, so it's not going to be an integer. And so what R does with that is that it still only allows it to increase by 1 each time, which means that our last number is actually going to be lower than what we specified. It's not going to go all the way through to 9.8 because the next integer value would be larger than 9.8. So it's kind of like Price is Right rules. It's going to stop at the closest one below our top number. Okay. So just to show that, gonna also go over our data types. So these are the same, just sequences using the colon operator. And you can see here again with going through 1 through 12.3, it stops at 12 because that's the closest integer to 12.3. And you can see that we can start with negative values as well, where it goes from negative 3.14, it then increases by 1 all the way to 6.86. And so there's differences in these classes. So with you can see we have 1, 2, 3, 4. We have a whole bunch of integers, and if we actually check the class on you, it is going to give us class integer. You don't really need to worry about that of what it means, but it means that everything in your data structure or your object is an integer. This is opposed to the class of D is actually numeric. So while the values in U are numeric, they are also integers, and so that's the class that gets assigned to it. Whereas in D, they're not integers, so it's just numeric. Again, you're not going to have to worry too much about that specific class type, but it is important to know that it is a separate class that R automatically assigns to any vector of all integers. And we can see that also in our environment, our studio environment, really. You can see the different types here. You have character, numeric, logical, numeric, and then integer is its own type. Okay, so next we are going to go over vector functions. Let me just make sure that's all. Oh, sorry. Right. So very important part. We have been looking at sequences that only increment by 1, and that's because we've been using the colon operator. But we can actually choose what we want to increment by. So maybe we don't want to increment by 1, but we still want to increment by some constant number. We can do that by using the sequence function, so seq, and then we have our start number, our ending number, and then this last third number, this is going to be what we're incrementing by. So what this is saying is that P is going to be a sequence that starts at 5, ends at 20, and increments by 2. So if we run that, and then run P, you can see that it goes from 5 to 19 because that is the closest increment of 2. 5 can't get to 20 in increments of 2, so the closest next number is 19, and so that's what it goes with. Q is similar. It's going to go, but this one is going to count down. So from 9 to 8 with increments of -0.1. And then if we see what Q is, we can see that it counts 9 to 8 can be counted in increments of 0.1, and so it counts all the way, counting down. I did also want to point out that what happens when you don't have the appropriate sign, is that R won't let it run. So if I get rid of that negative sign, and I have 9 to 8 with increments of 0.1, so it's a decrease in my numbers from my starting to my ending, but I'm trying to use a positive value of a positive increment, it's not going to actually let that run. And you can kind of get the gist of why it's not running when it says wrong sign in by argument. So it's telling you that positive sign on our positive 0.1, that's not working. You need to use a different sign. And so that should give you a hint if this comes up when you're trying to run something, that you just need to switch the sign and it will run again. So yeah, the same thing will happen if I try to use -2 here instead of 2. It'll throw the exact same error. Okay, so the class of P is numeric and the class of Q is also numeric, just to kind of give you a sense of that. Okay. So next we're going to get to vector functions. Okay, so now that we've talked about vectors and sequences, we can talk about vector functions. So the same way that we saw in previous videos, we were able to use different functions on our scalar objects. We can do the same thing with vectors. So there are different functions that are appropriate per each data type, which we'll see ones that are useful for matrices and data frames in the future. We've seen ones for scalars, and these are kind of specific to vectors, although you can do them to some other types of data. So the same way that we talked about scalars being like a point on a graph, vectors are like a line. In order to find the length of that line, all you have to do is run length on your vector. If you run that, you get 8. And another way to think about that is just the number of elements in your vector. So here we have 1, 2, 3, 4, 5, 6, 7, 8 elements in our vector, which means that the length is 8. So they are equivalent, the same thing. Number of elements and length of a vector is the same number. So if we have a numeric vector, we can run some other things on it. So these are this is stuff that we've seen in Excel and a little bit in SPSS, and so there are equivalents in R. Important to kind of remember or have jotted down somewhere what these are. So if we want to find out what the maximum of a vector is, meaning the maximum value of any element in our vector, we just run max on it. We'll get 13. If we want the minimum, we run that and get 0. The mean is 4.125. The median is 2.5. The variance is 19.5. And standard deviation is 4.42. And the sum, which just sums up each element in our vector, is 33. So very basic numeric functions. You can run them on numeric vectors. You can actually also run them on logical vectors, which we'll get to in a second. But first, I want to talk about rev and sort. So what rev does is it just reverses the order of a vector. So if we run rev on n, all it does is it takes our vector n here and it reverses the order. So now instead of going from smallest to largest in this order, it goes from largest to smallest in the reversed order. So what does sort do? First, I need to show you n. If we change the order up so that it's not actually already in the form of smallest to largest, but in a more random order. So let's say we have 0, 1, 2, 1, 5. Sorry. Oh, one sec. Do you want to do this now? No, I don't. Okay, let's hope that wasn't anything bad. That's what I get for not reading it. Sorry, so if we have 0, 1, 2, 1, 5, 3, 8, and 13. So these are all the same numbers that we had in our original vector, but now they're kind of in a randomized order. If we do rev on this, it just reverses the order. So it's not from largest to smallest, it's just a reversed order of n. However, if we run it on, if we run rev on sort n, what it's going to do is it's first going to sort n by smallest to largest, and then it's going to reverse the order of that resulting vector. So if we run that, we can see that we get the same thing we had before, where it's from smallest to largest in value, and the order of it is reversed. So that's what those ones do. Yeah, nothing super fancy. Okay, so if I'm going to set n back to what it was, just in case we end up using it in something. So I'm just going to set it back to the sorted version. And let's say we want to select specific elements of our vector. We can actually do that using our square brackets, which is, they're used for subsetting, or you can think of it as like selecting a specific set of elements from it. And so if we want to subset our vector, all we have to do is use our square brackets and then tell it the data location of the element we want. So we're not going to tell it, like, this is not saying that we want 5, 3, and 6 out of our vector n. This is saying we want the 5th element, the 3rd element, and the 6th element in that order of our vector n, right? So if we run this, we can see we get, and let me remind you what n is. So what is the 5th element of n? It's 3. What is the 3rd element of n? It's 1. And what is the 6th element of n? It's 5. So that's what that's doing. It's subsetting, specifying the location of the data we want, and then it returns it to us. We can do this with, so if you're specifying multiple locations, you need to use the C operator. Otherwise, it's not going to work. However, if you're using only a single number, so you're just specifying one data location, you don't have to use the C and brackets around it. You can just specify the one number. So if you remember, L was our logical vector we created of falses and trues. And we can subset that as well. All this is doing is saying the L square bracket 7 is saying we want the 7th element of L. If we press that, we get true. And if we count, we have 1, 2, 3, 4, 5, 6, 7. So this true is being returned to us because it's the 7th element of L. Okay. Also, like I said, you can do numeric-like operations to logical vectors. So the reason for this is what I mentioned earlier, where falses and trues can be read or coerced to numbers, where falses are 0s and trues are 1s. So if I do the sum of L, I'm going to add up each of these values, which these are just a bunch of 0s, so they equal 0. These are a bunch of 1s, so it's 1, 2, 3. So our sum is 3. And you can do all these similar operations. Anything you can do to a numeric vector, it will coerce a logical vector to 0s and 1s and perform those similar types of functions. Okay, moving on. Let's talk about operations to a single vector. So, right, we have used in the past objects as scalars. So we've assigned like an object name, just a single scalar, and we've used it in place of numbers. We can do that with vectors as well. So if we wanted to use a vector multiple times, we don't want to have to write out that vector each time. So we can just assign it to an object and then use that object like a vector. There are just, certain rules that apply and kind of ways that it works that we should go over. So W is just going to get 1 through 10. X is going to take W minus 5.2, and so the obvious question would be, okay, well, how does it minus a single number from a set of numbers? Does it do something to the set of numbers and then minus it? Does it minus it element-wise, or does it do something else? So let's run these. They're all just performing kind of simple functions, so taking the absolute value, returning it to a new vector, squaring it and rounding it to 2 decimal places, and returning it to a new vector. So remember, W is 1 through 10. x, how did it minus 5.2? Well, it minused it element-wise. So this is what happens to vectors when you're doing single operations to them. You're just going to do that operation element-wise to the vector. So likewise, y is just going to take the absolute value of each of the elements of x, and it's going to return it to a vector y of the same length. So you can see that it did just that. Z is then going to take those numbers in y, it's going to square each one, round it to 2, and return it each element to the element, a corresponding element of z, so that z will be the same length as y. Just like that. Okay, so this isn't in, oh wait, sorry, next one. This one is operations for 2 vectors. So we can then use vectors together to do operations with multiple vectors, not just one. We're going to go over just an example of 2 vectors, but you can do things with many, many more vectors than this. So G is going to get the sequence of 1 to 9, incrementing by 2, and E will get the sequence of 0 to 8, incrementing by 2. Just to give us a visual of what that is, this is G, this is E, and here, the first thing we're doing is checking if the length of these vectors are equal to each other. So a single equal sign is actually going to be like an assignment operator. However, a double equal sign is going to check for equivalence. So that is 2 equal signs next to each other without any spaces in between. So similar to our arrow here where there can't be a space, that's the same thing here. There can't be a space. It has to be directly next to each other for this operator to be read correctly. So this checks for equivalence. This is saying, is the length of G equal to the length of E? And the answer is true. And so because these are vectors of the same length, you can do operations to them very easily. So we add them together. It's going to add them together element-wise. 1 gets added to 0, 3 gets added to 2, 5 to 4, 7 to 6, and 9 to 8. And it's going to do the same thing if we do other operations. So we have E minus G times G, so first multiplying them together, then minusing, and G divided by the resulting vector of G plus E. And you can see all of the lengths of these are the same because the lengths are equivalent, right? So we're going to expect it to be the same length as our 2 vectors that we're using that are of equivalent length. So then this brings up operations with vectors that are actually of varying lengths. So here I've just created a simple, and this is not an example in the manual, I just wanted to go over it to kind of clarify. I think it's a natural question to then go, well, okay, what if they're different lengths? So here we have FF is just 1, 2, 3, EE is 1, 2, 3, 4. So they are of differing lengths. One of them is 3, one of them is 4. So what if we try to divide one of them by the other? We get a warning. It tells us longer object length is not a multiple of the shorter object length. And so we want to know, okay, but it still gave us a result. It didn't give us an error, it gave us a warning and a result. So what is that result? Here we have 1, 1, 1, 4. So what did it do? It took the first element of E, and divided it by the first element of FF. So 1 divided by 1 is 1, 2 divided by 2 is 1, 3 divided by 3 is 1, and then we have a 4. So how'd we get that 4? Here, it took this 4 and it recycled our smaller vector. So now we've used up all of our vector that we were dividing by, and so it gets recycled back to the first value. So now 4 gets divided by 1. If we had another value here, it would get divided by 2. If we had another, it would get divided by 3. And if we had another one, it would recycle again and go back to 1. And so on until it goes through the entire length of EE. So that's how it works with vectors of differing lengths. However, if it says it's not a multiple of the shorter one. So what if we have our shorter one is a multiple? The only difference here, so I just set it to be 1, 2. So now length 2 is a multiple of length 4. So if we divide it by that, we can see that it does the same thing. So 1 gets 1 gets divided by 1, 2 gets divided by 2, 3 gets divided by 1, and 4 gets divided by 2. So it does the same thing where it recycles it back in the exact same way. It's just not going to throw us the warning message because it is a multiple of the length of the longer vector. All right, so that's an aside. Last thing here for vector operations, we're going to go over basic just element updating. So you don't necessarily need to update an entire vector each time you want to make changes. You can actually just update single elements of it, which in practice is very useful. Here we have f is going to take a vector of 5 5s. Then we're going to take, let's just do that. Then we're going to take the third element. Remember, this specifies the number of elements. Sorry, this specifies the position of the element we want. So here we want to take the third element of f, and we're going to set that specific element to 3. Now we can see what did that do. It updated our vector f, so now it's 5 5 3 5 5. Okay, so it's just really simple updating of specific elements. And so you don't have to specify only single elements. You can specify several at once, the same way we did above with our concatenated string. So here we have t is 1 through 10, a simple sequence like that. And so what is this doing? This obviously looks a lot more complicated than this. So let's start from the inside. We have sequence 1 through 9 incrementing by 2. So let's remind ourselves, what does that do? It goes from 1 to 9 by increments of 2, so 1, 3, 5, 7, 9. And then let's check what this thing does. It's similar, but it's going to produce different numbers, right? So we have 0, 2, 4, 6, 8. So this first sequence here is being used to specify our data locations. So we're using our same square brackets, so we're subsetting, which means we're specifying data locations in our, or element locations in our vector. And those locations are going to correspond to the numbers in here. So what we're saying is we want to take the first, third, fifth, seventh, and ninth elements of t, and we want to set those to new numbers. The new numbers we're going to set are going to be 0, 2, 4, 6, and 8. So let's run this, and let's show what it is. So what did it do? It took the first element of t, and it set it to the first element of this sequence. So our first element got 0, our third element got 2, our fifth element got 4, and our seventh element got 6, and our ninth element got 8. So if you're kind of confused with something a little more complicated than this, what I suggest is always looking at the parts of it first, and then kind of logically working out, okay, I know that these square brackets mean that I'm calling specific data locations, so let me find out what the data locations are that I'm calling, and then I know that these are replacement values, so what are the values, and then maybe you can better figure it out. And before I get to loops, just wanted to point out quickly, so you can see that with all these objects that I've been specifying, like G, E, F, F, E, E, all of these are in black, right? Like every object that we write shows up in black, except for these. These are showing up in blue. So why are they doing that? I want to point out that capital F and capital T, specifically the capitalization, these two values already have a meaning in R. Capital F means false and capital T means true. So I'm following the example as it is in the manual to show this example, but I would just like to warn everyone that you should never, ever name your variables capital F or capital T. You can mess up what you're doing by doing that. So if you ever, see here that you're trying to make an object and you forget and you use capital F or capital T, you can see that it's in blue. That tells you it already has a meaning. Do not use that as a vector name. Do not use that as any object name. It already has a meaning, and you don't want to confuse R with the code that you're writing. Okay, sorry. So that's it for vector operations. Lastly, we're going to go over loops. Okay, our last piece for this video are for loops. For loops are really important. They are something I use every single time I code. And they are the other type of loop. So we talked about while loops. This is the other type of loop, for loops. And they're very similar. There's only a slight difference really between them. So what we're going to do is just walk through 3 of them, talk through the logic, and that'll be it. There are some example or some practice problems in the manual that I would totally suggest going over, especially for things like loops that people who don't use anything like R or aren't used to coding might not really be used to. So I would definitely take the time to familiarize yourself with it and with the logic of it. Okay, so for loops, the first example is 4.5.1, sum of square roots revisited. So first what we're doing is we're making a vector called even num, and it's going to be a sequence from 2 to 1,000 incrementing by 2. So this will go 2, 4, 6, 8, all the way up to 1,000. Then we're setting another object that is a scalar, and we're setting it to 0 to start. So next we have our for loop. So you start this with just writing out for. You can see that it shows up in blue here because it is a function, dark blue to be specific. And then you put in parentheses what you want the values, you put in parentheses the values you want this for loop to go through. So with our while loops, what we set up was a condition that needed to be met for the while loop to stop. Here, we know when it's going to stop because we're specifying the values for it to run through, which means we don't, it's not like a while loop where it stops eventually. It's a for loop, which stops within a set amount of time and a set amount of passes that are actually specified by us to start with. So here what we're saying is for some value, and val can be, again, like in our while loops, this could just be any kind of symbol. It doesn't have to be val. That's not specific to for loops. So what I very frequently do instead of val is I, and you'll see that a lot. So like I, J, K, those are used for loops a lot. But we'll stick with val for now. Sorry. And so what it's going to do is say for val in even num. Let me make sure that val isn't set to something. Val is 11, so that's fine. It'll reset. So for val in even num, and remember this is our sequence. So basically what it's going to do is it's going to go through 2, 4, 6, 8, all the way to 1,000. It's going to run this loop each time, and then it's going to be done. So what it's going to do, we're then specifying that again with our curly brackets, same way we did with our while loop. So this is what's actually happening in our loop. So result is going to take result plus the square root of our val, whatever our val is for that specific run of our for loop. So for the first one, result is 0, val is 2 to start with. So 0 is going to take 0 plus the square root of 2. Then it's going to go through to the next value in our for loop. The next one is going to be 4 because that's the next value in even num. It's then going to take result, which is now the square root of 2. It's going to take the square root of 2 takes the square root of 2 plus the square root of 4. And it's going to keep going through that until it gets to 1,000 for val, and then it will stop because it's the last number in our vector that we specified. So let's run through this. We've set even num. Let's show what it looks like. Why not? Boop-a-doo. It is 1 through 1,000 2 through 1,000 counting by 2s. Yeah. Okay. Our result starts at 0. We can see if we print out result, it's just 0. So with our for loop, for val in our vector even num, we're going to run result takes result plus the square root of val. Now we can see what is the result of that. It is 10,556.45. Okay, so that's all it did. It gave us a result. For loops are nice because they, you know how long they'll take to run. You don't have the issue that you have with while loops where you could potentially not trip your condition and it might not stop running. So for loops, you'll always know that they'll stop. You know when they're going to stop. So they're nice and predictable. Okay. Next example is rounding terms. So what we're doing here, instead of saying a sequence of differing terms, we're actually doing round pi is our object. It's a vector of just pi to a certain number of digits printed out multiple times, right? So this vector has the same value in it for each element. Counter is going to start at 1 here. And our for loop is going to take for val in round pi, right? So it's going to go this number, this number, this number, this number. What it's going to do is it's going to take round pi. It's going to then take the element specified by counter. So if counter starts at 1, in our first round, what it's going to do is it's going to take round pi element 1, which we can see is 3.14159, which all of them are, but it's this one specifically. It's going to take that value and it's going to round it to the value. So, right, remember, round takes a value and rounds it to the number of decimal places specified. So, because val is going to be pi each time, it's going to take pi and then it's going to round it to the number of digits specified by counter. And then counter is going to update by 1. So what we should get is pi multiple times, all with a different number of decimal places. So let's run that and see that it works. And it did. So here we have pi rounded to 1 decimal place. That's because our counter started at 1. Then it's rounded to 2 decimal places, then 3, then 4, then 5. So it worked exactly as we thought it would, which is always good. Okay. It's also good because it's important to know what your for loop is supposed to be doing, because that way you can actually check it for errors. All right, last example. I know this video is long, so thank you for sticking with it. This is example 4.5.3 called Power Tower of Order 2. And so what we're doing is we are setting an object named Power Tower, the sequence of 1 through 11 incrementing by 2. Again, I think it's helpful sometimes to see what we're using. So it's 1, 3, 5, 7, 9, 11. And then our counter is just getting set to 1. Next, what it's going to do is it's going to be a for loop for val. Again, val is just any object name that you're specifying that doesn't already have like something else you're using. I mean, it'll overwrite it if it does have a value. But anyway, so val in Power Tower, which again is our sequence. So val is going to cycle through 1, 3, 5, 7, 9, and 11. Then what it's going to do in each cycle of this for loop is it's going to take Power Tower. It's going to do a similar thing of what we did up here, where it's going to take the number element specified by counter. So the first time it's going to take the first element, and then it's going to set that to val to the power of that value, right? So for the first one, we're going to have 1. This is going to take 1 to the power of 1. It's just going to be 1. However, for our second value in this sequence is 3. What this is going to do is it's going to take our second value, 3, because I forgot to say counter then updates itself by 1. That's an important part of the loop, and goes back through. So the next value is 3. It's going to take Power Tower 2, so the second position, which is 3, and it's going to then take 3 to the power of 3. So 3 cubed will then be the second element in our resulting Power Tower. So let's run through this. And what did we get? All right. So we got 1 to the power of 1. We got 3 to the power of 3. We then got 5 to the power of 5. And we can check that, right? Like, we get the same number. Yeah, and so on as it went through. So basically, for loops, you can do a lot of things with them. They get a lot more complicated than this. But the basic thing is that you are specifying a sequence that you want to walk through and do the for loop for every value in the sequence. Oftentimes this sequence does increment by 1, but it doesn't have to. And so for each value in a sequence, we want to do something. And that's pretty much it. That's all a for loop does. It's simple, but it's super, super powerful. It does a lot of things when actually coding. So very important to know. All right, that is all for this video. Thank you for sticking with it. We have a few more for the rest of the week.